All right, welcome everyone. In the next set of videos, we are going to take a look at this notion of what does it mean for a set of vectors to be linear independent. And before we do that, I want to just make sure that we are comfortable moving around between different representations for systems of linear equations. So let's consider M by N matrix A. And we're going to let A1, A2 up to AN denote the column vectors of this matrix. So these are bold fonted vectors. So each of these vectors has M entries, right? Because there are M rows in this matrix. And let's consider the homogeneous equation matrix A times vector X is equal to the 0 vector. And recall that this matrix equation based on how we defined multiplication between a matrix A and a vector X is equal to this vector equation where we're going to take x1, which is a scalar, the first entry in vector X, times column vector 1 of matrix A, plus x2 times column vector 2 of A, all the way up to xn times the last column vector of matrix A, and we set that equal to the 0 vector. So this also is bold font 0 vector on the right side. So when we set the right side equal to 0, we call this a homogeneous matrix equation. And this matrix equation is equivalent to this vector equation, which is equivalent to a system of linear equations with the following augmented matrix below, where again, all of these things are bold fonted. So we're thinking about these as column vectors. So this is the first column vector of A, the second column vector, and then we have the last column vector consists of zeros. So let's review a couple of important points about these systems. So first, recall that there's always one very obvious solution to a homogeneous equation, which is the trivial solution if we were to set all values for each of the variables equal to 0, we'll certainly get the 0 vector over here. So we're usually curious whether or not we have non-trivial solutions. So a non-trivial solution would be where at least one of these x's is not equal to 0. And so if that is the case, we'll see an interesting ramification of that is then that means one of these column vectors can be written as a linear combination of the other column vectors. And so what I've shown above is without any loss of generality, if we were to assume that x2 were not equal to 0, then we could subtract that from both sides, which I've shown over here, and then we could divide both sides by x2 because we've assumed this is not 0, and now we have vector A2, column vector A2 expressed as a linear combination of the other column vectors. And on the other hand, if a trivial solution is the only solution to this homogeneous matrix equation, then that's going to imply that it is not possible to take any one of the column vectors of matrix A and write them as a linear combination of the other column vectors. And so let's dig a little bit deeper into this connection between solving the homogeneous matrix equation, AX is equal to 0, and what that tells us about the column vectors of matrix A. Okay, so let's consider the following homogeneous vector equation. x1 times the vector 2, 1, 0, plus x2 times the vector minus 1, 6, 3, plus x3 times the vector 6, minus 10, minus 6. All of that is equal to the 0 vector 0, 0, 0. And we want to see whether this vector equation has a non-trivial solution. Clearly setting x1, x2, and x3 all equal to 0 will be one solution that we call the trivial solution. So if we want to solve this vector equation, because it's equivalent to a system of linear equations with the following augmented matrix, which has top row 2, minus 1, 6, 0, and then the second row is 1, 6, minus 10, 0, and then the third row is 0, 3, minus 6, 10. So we can work with this augmented matrix. We can perform row operations to put that into reduced row echelon form. So, we could use Python and we can use Google Colab to find the reduced row echelon form using the SymPy library in Python. So however you want to do this, we can do some row operations. You should be able to reduce this matrix to the following form. And so notice in this form, the first column has a pivot, the second column has a pivot, the third column corresponding to x3 does not have a pivot. So we have a free variable, and this means that we are going to have a non-trivial solution would exist for this vector equation up top. So this vector equation has a non-trivial solution. What is that going to tell us about the relation between the column vectors 2, 1, 0, -1, 6, 3, and 6, -10, -6? Okay, so on the previous slide, we took the augmented matrix for this vector equation. We found its reduced row echelon form. There was a free variable corresponding to x3 since the third column does not have a pivot. So from this form, this reduced row echelon form, we can get the solution set, namely that x1 is going to equal, when I bring this to the other side, -2 times x3. And this row tells me that x2 needs to equal 2 times whatever x3 is, and x3 is a free variable. So this gives us the following solution set, namely that x1, x2, x3 is going to equal any kind of scalar multiple of the vector -2 to 1. If I factor out the x3, we get this nice vector form for the solution set. And this means we have this homogeneous equation that we started with has an infinite number of solutions. And let's just pick one of them, namely if I were to pick x3 is equal to 1, then that would mean x1 is equal to -2, so I can plug that over here. x2 would be 2, and x3 is 1. So that means this is one possible non-trivial solution to this vector equation. And then we could think, well, what does that tell us about the relationship between these three column vectors? And this means that I can take one of these column vectors, for example, this last one, and I can express it as a linear combination of the other two column vectors. So bringing this to the other side and then dividing by -1 gives us this relation that the vector 6, -10, -6 can be written as some linear combination of the other two column vectors 2, 1, 0, and -1, 6, 3.